Hello, myself Pallavi. I'm a student of MTech Photonics first year. I'm going to present my video PPT on finding errors in numerical computation and Taylor series using MATLAB and submitting this video PPT to Associate Professor Mayank Goswami, Department of Physics, IIT Roorkee. So first I'm going to give you an introduction about what are numerical methods. So numerical methods are capable of handling large systems of equations, non-linearities, and complicated geometrics. The main aim of numerical methods is to provide constructive methods for obtaining answers to such problems in a numerical form with the following characteristics like efficiency, accuracy, numerical stability, and rate of conversions. So, why the numerical methods is important, why we need this numerical method. So, let's see. So the importance of numerical method is that it plays a very important role in solving real life mathematical, physical and engineering problems. In the field of science and engineering complex, mathematical problems are solved using methods and algorithms of numerical methods. This has helped both the field to tackle the complex numerical in a more relevant and accurate way to obtain desired solution. So while calculating such complex mathematical problems using numerical methods, the errors are introduced during the process of implementation. So there are two types of errors that are introduced. So these are the first one is round off error and the second one is truncation error. So round off error means it arises when a fixed number of digits are used to represent the exact number. Such numbers need to be rounded off to some near approximation which is dependent on the word size used to represent the numbers of the device. And the truncation error is that it is raised by using approximate results or by replacing an infinite process with a finite one. It is the type of algorithm error that is procedural error which we can predict the extent of the error that occurs in the method. So in this presentation or in this video, I'm discussing more about the truncation error and by using and with the help of Taylor series, we are going to see how the truncation errors are introduced in the Taylor series and how these are related to the number of terms and the step sizes that we are going to take in the infinite series. So this is the expression for Taylor series, that is f of x plus h is equal to f of x plus h f dash x plus h square by 2 factorial f double dash x plus and so on with the order of error h to the power n plus 1. Here x is any particular value that we are going to take, h is the step size, and this dash double dash represents the first derivative, second derivative, etc. And here the order of the error is represented as h to the power n plus 1. Here h is the step size and n is the number of terms that we are going to take in a particular expression. So that means the error introduced is equal to h to the power n plus 1. So, so here we discuss about the Taylor series. Now the point is that why we are talking about the Taylor series. So what is the importance of Taylor series? So the importance of Taylor series is that it helps to show how a complex function behaves and is used in physics and chemistry. It gives the sum of the function at some point that needs to be evaluated and all of its subsequent derivatives. This means every additional sum will have a power higher than the previous one. So this is the importance of Taylor series. And in the expression of Taylor series, when we put x equal to 0 and taking step size is equal to a, we get the Maclaurin series. So this is the Maclaurin series that that I have written for exponential of a. So here we take x is equal to 0. So by putting x is equal to 0 and taking step size is equal to a, we get the Maclaurin series. So this is the nth order uh, term expression for Maclaurin series. So e to the power a is equal to 1 plus a square by 2 factorial plus a cube by 3 factorial and so on. And the order of the error is a to the power n plus 1. So here a is the step size and n is the number of terms introduced or number of terms that we are taking in the expression. So by So with the help of MATLAB coding, I'm going to discuss how the errors are related to the step sizes and the number of terms that we are taking during the expansion of the infinite series. So this is the code that I have written for that I have write for Maclaurin series for exponential of a. So n equal to 3. So n equal to 3 means this defines the number of terms that we are taking. So here I have take n equal to 3. We can take any value of n. And a all, it gives the different values of step sizes. So here I have take four different values of step sizes, that is 0 0.1, 0 0.05, 0 0.02, 0 0.01, and defining a vector 1 to n. And this is the error vector, and here I have take the error vector as null vector. Now using for loop to complete this code. So here I have take I is equal to 1 to length of a all. Here a all is the uh, values different values of the step sizes that we have mentioned earlier. So a is a all I. That means we are taking the all different values of step sizes, and there are various terms that are appears in the expression, which is a to the power n. So here a to the power n means we take a to the caret of vector that we have defined earlier divided by the factorial. The factorial is to be calculated by using the MATLAB command comprod. So here we use dot slash. So dot slash is used because we need element to element divisions. So these are the terms that appears in the series. And x, well, it is the it gives the value of Maclaurin series for given exponential term. This is 1 plus cum sum terms. So cum sum is the MATLAB command. It gives the sum of all the terms that are included in the series. And this is the true value of the exponential that we have take. And this gives the errors that are introduced. So this is the code for plotting the graph. So we are plotting logarithm of different values of step sizes and the errors that are introduced. And this is the labeling of the graph and giving title of the graph and legend we use to specify three different lines in a single graph. So this is the output of the graph. So we have three different curves, linear curves for n equal to 1, 2, and 3. So as we have observed from the graph that as we increases the number of terms, that is n equal to 1, 2, and 3, the error also decreases. And with the increase of step sizes, as we increase the step size, error increases. So from this graph it is clear that if we increases the number of terms, the error decreases, and if we increases the step sizes, error increases. So now let's see what important conclusion that we get from this graph. So for different values of n, we get these curves, which is linear, and we can easily find the slopes of these three different curves. So slope for the different values of n is that for n equal to 1, slope is equal to 2.013. That means we can say that slope is equal to 2. For n equal to 2, slope is equal to 3.00985. That is equal to 3. For n equal to 3, the slope is equal to 4.00787. That means we can say that slope is equal to 4. So an important conclusion we get from this calculation of slopes is that for nth order, the slope is equal to n plus 1. See, for n equal to 1, the slope is equal to 2. That means slope is equal to n plus 1. That is 1 plus 1 equal to 2. For n equal to 2, the slope is 3. That means slope is equal to 2 plus 1. That means n plus 1. For n equal to 3, slope is equal to 4. That means slope is equal to 3 plus 1. That is n plus 1. So, the important thing is that for nth order, the slope is equal to n plus 1. So to summarize, what we see in truncation error is that when we have more number of terms, that means if we increases the number of terms, that is n increases, the error is lower in that case. And second point is that if we take the smaller values of a, that means if we decrease the step sizes, in that case also we get lower error. And when we plot graph between log of error versus log of step sizes, the graph increases linearly, and the slope is n plus 1, which is the order of accuracy. So these are the references that I have taken to explain these concepts, and I hope this presentation will give some idea about the truncation errors and how these errors can be calculated, or how we can reduce the errors by increasing or decreasing the number of terms and step sizes in the expressions of infinite series. So I'm going to end this presentation here. Thank you.